We can start. Hi, everyone. Welcome to the C3 AI DTI seminar series for the fall semester. My name is Gauri Joshi. I am an associate professor at Carnegie Mellon, and I'm co-organizing and co-hosting this semester seminar series with Richard Zhang, who is an assistant professor at the University of Illinois. So before we begin, we would like to pause to acknowledge the support from our academic and industry partners, for which we are deeply grateful. And our fall seminar series is organized around two special themes, adversarial machine learning and distributed and federated learning. And our talks are scheduled to alternate between these two themes. So today is the first talk on distributed and federated learning. And after today's talk by Professor Suvrit, we also have a really exciting lineup of speakers in the coming weeks. We'll be hearing from Bo Lee from UIUC, Brendan McMahon from Google, Zico Coulter from CMU, and Eric Sheng also from CMU. Our series will extend all the way to December with the speakers featured here. You can find the details of the speaker information and the abstracts on our website. Also, the videos of the previous talks, both of the current series as well as past series, will be available on our YouTube channel. We invite you to subscribe to our newsletters and our channel so that you don't miss these talks. So without further ado, today we are very happy to welcome Professor Suvrit to share his research with his talk entitled Two Surprises When Optimization Meets Machine Learning. Professor Suvrit is an associate professor in MIT ECS. He's a core faculty member in IDSS and LIDS. His research lies at the intersection of machine learning with mathematics, spanning areas such as differential geometry, matrix analysis, convex analysis, probability theory, and optimization. And he founded the Optimization for Machine Learning series of workshops in 2008 at NeurIPS. And he is also a co-founder and chief scientist of MacroEyes, a global OR plus optimization plus ML healthcare startup. So I'll hand off to Suvrit. The talk will be about 50 minutes. And for the audience, please use the Q&A feature in Zoom to submit your questions. We will ask the questions to the speaker on your behalf at the end of the talk. So that's it from me. I'll stop sharing, and Suvrit, you can take over and start when you're ready.
Okay. Thanks, Gauri, and thanks to the organizers for inviting me. And it's first talk. And the topic is actually something very basic. And as Gauri announced during the semester, there's an exciting lineup of talks at the optimization ML boundary and related areas. So I thought, okay, maybe to contextualize, I'm going to talk about something very, very basic to optimization. And it's so basic that it's almost like going back to high school and talking about f prime equal to 0, what happens. And interestingly, that's where the surprises begin. So optimization for optimization plus ML is a very active area. And as Gauri said, I co-founded that OPT series of workshops. It still happens at NeurIPS every year, almost every year, and probably will happen this year too. So many of the audience may be interested in participating in that. I no longer co-organize it, but I have a strong interest in the future of that workshop. So I work a lot in variety of optimization questions. And one of the important ones for me is theory of optimization as specifically of interest in deep learning. understanding how we train deep neural networks, how to train them better, or why certain heuristics work, can we bless them theoretically, or looking at what happens when you train deep neural networks using existing methods and seeing that, oh, are there some very interesting phenomena that are happening that current theory does not manage to explain? Can we develop new theory? So that's kind of the rough context. And I want to share surprises with you, and you'll see that, yeah, okay, some of the surprises, depending on your background, they may be big surprises to you. Some of them may be small surprises, but I hope they're surprises nevertheless. And the stuff that I'm talking about right now is based on joint work with my PhD student Jingshao Zhang. He's actually graduated now. He's faculty at Tsinghua University, and other collaborators, Hongzhou Lin, Professor Stephanie Agelka at MIT, and Professor Arijat Babai also at MIT. Okay, so let's just begin and dive right into where the surprises are coming from. So just to set the stage, please excuse the super mundane slide, just to remind you that when I'm talking about an optimization problem, the focus of today's talk is purely on somewhat on the theoretical side, but on very high level theory side. So what's an optimization problem? You have an objective function, here written f of x. You may have some constraint, let's not worry. And we all know it captures things like linear programs used all over, or integer linear programs used all over in OR, combinatorial problems and whatnot. For us of interest, it's the heart of machine learning. And within machine learning, out of many things, given the current interest, focus being on training neural networks, where the problems take a very specific form. The cost function that we are trying to minimize is a sum, or rather it's an average of simple cost functions, and n denotes the number of training data points. This is a so-called empirical risk minimization problem. So what's special about these? Well, what's special about these is that in machine learning, almost all the time, we are trying to minimize that sum of cost functions, and we're trying to minimize it using essentially some version of so-called SGD, stochastic gradient descent. Most of you may have heard of that name. And it's broad family of algorithms which have a very simple structure. X is your guess of the parameters, which would be the weights of a neural network, for instance. And you iteratively update them according to eta being some kind of learning rate or step size, and G is a vector which tells you which direction to go into. And G could be the full gradient, then you get gradient descent. It could be a vector which in expectation is a gradient, you get stochastic gradient descent, that's the de facto choice. And it could also be some kind of subgradient when things are not differentiable, etc., etc. But the kinds of optimization methods we use in machine learning, they take roughly this structure. I'm simplifying some details. And when we start trying to study theory about these methods, the first kind of question that comes to our mind is, does it work? What does it mean for it to work? Does it converge? And if it converges, of course, we have to define what we mean by converge. Then we have to, next question we may ask is, okay, how do we measure? Is it converging quickly? Is it converging slowly? You have 5 different methods in front of you. Which one is converging faster? So you have to define a notion of faster, and so on. And all of this was nice and good as long as you're doing convex optimization. But the moment you're doing non-convex optimization, judging convergence becomes tricky, because you can see with, this is a pretty simple landscape. It's riddled with saddle points, local maxima, local minima, and other such points. And we know that in general, non-convex cost functions, of which deep learning cost functions are examples, in general, it's intractable to even optimize them to reach a local minimum. Forget about going to a global minimum. You may already know that, even recognizing that you're standing at a local minimum is NP hard in general for non-convex problems. So what we do we make a compromise. We say, okay, fine, doing theory of global optimization, etc., having a useful theory, that is, can be pretty hard. So let's do something much simpler. Let's lower the standards drastically and ask simply for satisfying a necessary condition. So this is what I meant, f prime equal to 0 from high school. If you have a cost function, we know it's hard to go to its optima. You may reach them if you're lucky. That's a separate branch of theory. But in general, let's say we lower our standards and say all we want to do is ensure that you at least satisfy a necessary condition of optimality. Right? And this is the divide between convex and non-convex optimization, that the simple first order gradient equal to 0 condition is necessary and sufficient in convex land, and in non-convex land, it's only necessary. So that's a huge divide. So we try to satisfy that. And then we try to judge convergence or quality of methods, or try to understand their theory. And by we, I mean the entire community, okay, not just me, on how well or how quickly can we satisfy this necessary condition. So the leading theoretical model for this is inspired from convex optimization, and that's called oracle-based complexity. So what does the oracle-based complexity model say? It has a very simple structure. It says, well, I have access to a subroutine, which maybe I programmed or you programmed or we downloaded it from GitHub, whatever. That's a black box. I give it X, which is my current guess, and it returns gradient of f of X, or a stochastic gradient or something. So that means you have a subroutine that can generate essentially gradients for you. So this is the first order oracle. And what we try to do is we try to count how many such gradients would you have to generate to satisfy the optimality condition. Right? So this is the standard way of comparing a million different algorithms, which one is better, which one is worse, in terms of who can, by consuming the smallest number of gradients, get me closest to a stationary point being where gradient is essentially 0, epsilon stationary point, right? And this paradigm is the framework in modern analysis and optimization, and it's been very successful. It has led to the discovery of important algorithms like Nestrov's accelerated gradient methods, or variants of path following interior point methods. And it gives us dimension-free rates. You don't have to worry about that, or you don't have to worry about, did I implement using autodiff a better subroutine for gradient f than somebody who didn't do autodiff? So you hide that away. And more importantly, the kind of computational complexity analysis that has been very valuable and of great interest in our community is that it's non-asymptotic analysis. So you're not saying in the limit of infinitely many iterations what happens. You're saying after 10 steps, after 100 steps, where is your method? How close to done are you? So all of that is good, except and based on that good framework, there's also been a lot of progress in non-convex optimization. So you look at this cost function, training loss of deep neural network is a special case of this cost function. And don't worry about this plot. All I want to say is that there were some theorems proved in 2015 on how quickly you could reach a stationary point of that cost. And then somebody proved lower bounds also, but within 3 years, tight results. There was a lower bound on how many iterations are absolutely necessary to come epsilon close to a stationary point. And there was some upper bounds on constructing methods that take a certain number of iterations and come close to stationary points. And that got pretty quickly closed. And you'd say, wow, okay, near optimal stuff has happened. And it applies to, as I said, to deep learning as a special case. Now, everybody, of course, who has worked with deep learning, or even those who haven't worked with deep learning, may already be wondering, so, okay, there's an obvious caveat here, right? And really, that's the caveat which drives pretty much most of my research in deep learning theory, is trying to understand and reduce this gap between theory and practice. So the theory result I already showed you, but in practice, deep learning is posing all sorts of interesting challenges. And a large number of those challenges, they are not only coming from how you training a deep neural network is the same as solving that optimization problem. They're not only coming from how you train a deep neural network, but they're also coming from the divide between training and testing. Often when we derive a lot of theory to develop a faster method, it's really focused on the optimization problem, sometimes ignoring the statistical problem that machine learning actually cares about. That is, I want to learn a mathematical model that works for unseen data. And given this non-convexity and all sorts of complications, it's not always clear how to translate from training to test. It remains an open issue for our community, right? But nevertheless, as a result, something very interesting happens. Methods that are theoretically optimal, and they do work quite well also for many training problems, end up learning parameters of your neural network model, which don't work that well on unseen data. So here the y-axis is test error, and our friend, good old stochastic gradient descent, ends up outperforming more fancy methods, even though theoretically SGD is inferior. This is the common picture, right? Whereas there's more examples in there. So here SGD was theoretically inferior, and it ended up working better. Another related method is, which you certainly heard of, is like some method like ADAM or other such adaptive gradient methods with momentum and whatnot. Theoretically, you can show that they fail. Even for one-dimensional optimization, they can fail. But in practice, they're very widely used and they work very successfully. So again, that's a huge divide in the other direction between theory and practice. And once you reach this stage, you say, okay, so theory, the upper lower bounds are close, but empirically fast methods are theoretically divergent, and theoretically not so great methods are empirically great. So what's going on? So of course, for a person who's researching in this area, it's a great news. The less that is known, the better it is for us, because there's more for us to work on, right? And what I'm trying to say in today's talk is that we actually are at a stage that we need to rethink entirely how to do optimization in machine learning. Because the standard approach, the standard ways of doing things have brought us to this theory practice gap, which seems to be not resolvable by the standard thinking. So time to take a step back and think about very fundamental questions once again. Really, and by fundamental, I mean really very, very basic, like gradient is equal to 0 style of questions. And that's what I'm talking about here to set the stage. And these concerns, they get even more magnified in this distributed and federated and such setups that I care for also. But let's just look at the very basic concerns. And they're driven by two surprises, which shouldn't really be, okay, the second one should be a surprise, but the first one shouldn't be a surprise. But the surprising thing is that it's ignored so frequently. So the first surprise is ignoring the elephant in the room, SGD. You can see I colored G in red, in bold, to say, what does SGD stand for? Stochastic gradient descent, right? And that's where the first surprise comes up, is with the handling the G. And the second surprise, which I will just share with you later on in the talk empirically, is that actually there are many settings where neural network optimization doesn't converge in the sense of theory, which is very interesting. lays open the challenge for all of us to ask what to do. So let me tell you the first surprise. It's almost a tautological kind of surprise, but it is worth knowing about, is the simple surprise. So let's recall standard analysis of our friend stochastic gradient descent. Essentially, this template, the starting point template of understanding SGD, you'll find in hundreds and hundreds of papers over the past many decades on SGD. It's this iterative process, right? You iteratively update the parameters, all right? And even in the most restrictive setting, what happens? Boom. We say, well, we are doing stochastic gradients, so we assume a cost function is differentiable. And not only we assume it's differentiable, we assume its gradients don't fluctuate too much so that we can get a handle on how useful the gradients are. And that's called the Lipschitz smoothness assumption. So these types of assumptions are, of course, introduced often for the convenience of the mathematical analyst in the room, because we like to compute Taylor series expansions to see what's happening. And then you compute a Taylor series expansion, and then you bound some terms, etc., etc. You don't have to worry about the details here. I just want to show you a template of the proof, okay? That the update is like that. We assume things are differentiable. We assume the gradients don't fluctuate much, so the cost can be upper bound locally by a quadratic. Then you plug in xk plus 1 as that update, and you do some simple rearrangement. And you assume that the hard part, which we don't know how to control, the norm of the gradient is bounded by some constant. So I'm just trying to oversimplify. This is the most oversimplified analysis of stochastic gradient descent with some kind of step size. It shows that, whoa, okay, after t steps, you are within 1 by, so the rate of, 1 by square root t, that's the rate at which you are shrinking the gradient. So stochastic gradient descent in expectation shrinks the gradient so fast. And really, this is a 4 or 5 line analysis. And it's actually, in the worst case, optimal. You can't do better than that. So SGD is doing the right thing. And the standard analysis, if you think critically, or just, you think practically, is this analysis even applicable to the neural networks that people are training? Are things really differentiable, L smooth, etc.? Are they? Well, the first failure, even if we had some kind of Lipschitz-ness and we could pretend things are good, well, the standard analysis of SGD insists on the letter G. It assumes differentiability. But how many of you have tried out, say, a ReLU neural network? ReLUs are not, they're widely used, right? They are not differentiable. It's max of 0, x. That function is not differentiable. You put a deep neural network with a composition of so many of those, things get even hairier. So so you have non-convexity and non-differentiability. And you could say, okay, fine, maybe I'll just use activations that are differentiable, or maybe I'll work with only infinitely differentiable transformer models or whatever, fine. But I'm saying that even though for so many years ReLUs have been used, pretty much every paper that gets written hides the fact, when doing analysis for training neural networks, hides the fact that things are non-differentiable. Is that a good thing or a bad thing? Well, if you want to be theoretically rigorous and you want to develop theory which doesn't increase the gap between theory and practice, but helps reduce the gap and helps show us probably the step forward, that's valuable to pursue, I'd say. So that's the first surprise. It's coming up. The surprise is mathematical, but the zeroth order surprise here is that, well, everybody has used ReLU neural networks, but all the theory that people publish, they publish by assuming differentiability. So it's surprising that this thing gets ignored so blatantly. So what we'll assume now for simplicity is, okay, let's assume that the loss function is Lipschitz continuous. So it doesn't, at least locally, so it doesn't fluctuate insanely, or maybe, it's not discontinuous. So there's some hope of optimizing it. And we're not going to assume it's differentiable. And in this case, interesting things happen. If you have convex optimization, then for smooth functions, it's known you can optimize them faster. You can see this rate is faster. Epsilon is a small number. And if they're not smooth, which means they're not once differentiable here, but they are Lipschitz continuous, you can still optimize them, but much more slowly. In the non-convex case, smooth functions, you can optimize at some provable rate to stationarity. This is to optimality. But I don't know what happens in the case they are non-differential. Stochastic case, same story. The moment you have non-convexity and non-differentiability, we don't know what comes in there. And the surprising thing, there is a surprising thing that comes in there. And it's not like, the surprising thing is it's not just, tweaking a little bit of analysis and you can somehow fill in the table. Surprisingly, that doesn't happen. I don't have time to go off on a tangent here, but some of you may do pattern matching and try to see how stochasticity and non-convexity and non-differentiability, they are kind of analogous concepts, but that's kind of a meta statement. So when the cost function is non-smooth, so in optimization and machine learning, by smooth, we mean once differentiable. And of course, in real analysis, when people say smooth, they mean C infinity. For us, we only care for once differentiable when we say smooth. So if your cost function is non-differentiable, non-smooth, then there's a variety of conditions and assumptions and structures that exist for the non-convex case that people have studied in the literature. There's hundreds of papers on these types of settings. There's some kind of Polyak-Loyasevich condition, or it is the loss is smooth, but the regularizer is non-smooth, but the regularizer is convex, and all sorts of other setups. Tame functions, stratifiable functions, semi-analytics, what all kinds of cocktail of assumptions exist in the literature. And luckily, for practical purposes, the larger class of essentially locally Lipschitz suffices. But for the purpose of, okay, let me not go deep into that in the interest of time. What we will care about are actually so-called functions that are differentiable in every direction. And the takeaway for you that I'll tell you here, so what you want when you want to develop a theory of non-convex, non-differentiable optimization, one thing which I'd like to have in there is, well, this theory had better be applicable to deep ReLU network. That's kind of my only requirement. On the mathematical side, what that means is, well, a neural network is composed of layers, right? And layers means composition of functions. And when we kind of try to differentiate a composition, that's where our friend, the chain rule, comes up, right? So you kind of want to look for a large class of non-differentiable, non-convex functions for which some kind of chain rule holds. And that's the rule that often fails for arbitrary non-convex functions. Okay, so chain rule is crucial to the success of backprop, etc. Right? So that so that's at the high level, the class that matters. And there's all sorts of results that exist, some asymptotic results, some lower bounds, and this and that. And this is a very active area currently. But what is not known is, unlike that table that I showed you, which said to reach an epsilon optimal point, you need 1 by epsilon square calls to the oracle, or 1 by square root epsilon, something, or 1 by epsilon to the 4 calls to the oracle. such type of complexity analysis is unknown in the non-convex, non-smooth case, because the problem is not that well defined. And the reason is, well, in the convex case, gradients can be replaced by subgradients. So you can see this at point A, this function is smooth. There's a unique tangent that gives us the gradient. At point B, it's a corner, a kink, so it's non-differentiable there. So there's an infinity of these lines, which are like subgradients, which all suffice to help you do optimization. And that's really great thing for convex optimization. And reason is because these lines give you global underestimators of functions. Flip this graph on its head and pretend it's a non-convex function, and suddenly you may not have any such lower global underestimators. So it's a rather messy area, the non-smooth calculus for non-convex functions, but it's been kind of well studied. There's some very good candidates, etc. there. Let's not worry about those. Let me now start quickly coming towards the actual theoretical surprise. The surprise is this: finding even a stationary point is hard. We already lowered the game from trying to even get to a local optimum. We made it even simpler. We said we just go to a stationary point where a necessary condition is satisfied. And the surprise for us was, okay, the moment you try to study this class of non-convex functions, which includes ReLU networks, finding a stationary point is also hard. And what you'd like to do there is, you want to find, because you want to find at a stationary point, the zero vector for a differentiable function, gradient of f equal to 0 will be the stationary point, right? And epsilon stationary would mean norm of gradient is less than epsilon. Well, in the non-differentiable case, you'd say there is a suitable notion of generalized gradient or subdifferential here, and you want to find something whose small in norm vector, a vector, smallest norm vector being less than equal to epsilon, right? So you want to find that. This is a very weak thing. And it turns out that by looking at these functions that have this non-differentiability, you can see that this function is, of course, differentiable everywhere, but its gradient doesn't have much information. Either it's +1 slope or -1 slope, no matter how close you come to 0. And only at 0, you'll actually have a 0 available to you, right? So this gave us the idea that we can construct a bad oracle. And these things are called resisting oracles. And the idea is, because you want to minimize your function, how do you minimize? Each time you call a subroutine called the oracle, which gives you back here some kind of generalized gradient. Because these things are not differentiable, you have to replace them with suitable generalized gradients. And what we showed is you can construct a really bad function or a bad oracle, which essentially at every step just gives you back a 0. And for any finite set of queries, it manages to give you back a 0 and give you back a boring constant number as the gradient by actually constructing a pair of functions whose stationary points are far away from each other, but no number of finite queries will help you distinguish between these two functions. So as a result, you can show that there exists no finite time method that can give you an epsilon stationary point for a non-smooth, non-convex function. And that's quite disturbing to us because we thought stationary point was the simplest thing to be doing, and you can't even find that, which led us to introduce a more general notion of stationarity, which says that rather than just look at the subdifferential at point X that you want to be stationary point, you look in a bigger neighborhood around that, saying that, okay, getting to a stationary point is hard. What if we make a big ball around it? Maybe we can land in the ball. Maybe that's easy. And it turns out even landing in that ball is not easy. You may have to compute number of gradients that depends exponentially on the dimension of the data. So even after making it even weaker, it remains tricky to come epsilon close to stationary point. There is then a version that we introduce, which actually ends up being something in the literature called Goldstein Sub Differential, which says, no, don't only look at all the points in a ball, take also their convex hull, which would basically mean, the ball would correspond to just these two arrows, and the convex hull means include all the vectors in between. So sort of like an even bigger, much bigger set, if these arrows were the extreme points. And it turns out for this much larger set, which we call delta epsilon stationary, we can prove something. And don't worry about all the technical details. The key thing to note here is, one, basic notion of stationarity is not attainable by any finite time method. A simple extension of that to just make a ball around a stationary point is also not tractable. So a third notion, which has been previously interestingly studied in the literature, turns out to work. And that third notion turns out to work in a very surprisingly interesting manner, which I'm about to tell you. And by the way, in case of differentiable, if things are differentiable, et cetera, you recover the usual stuff, which is a sanity check. That convex hull proves to be very interesting. And so differentiability was a hurdle. Of course, once you didn't have differentiability, you don't have Taylor series. So if you want to analyze algorithms and you don't have Taylor series, you have to work harder. And the way we get around that is to use randomization, but we use randomization in a very careful manner to avoid depending on dimensionality of the problem. So it's not just smooth everything with the Gaussian isotropically, and then you'll have to pay price of dimensions. We don't want to do that. So anyhow, let me skip this part and actually tell you what the actual algorithm that pops up, okay? And this is the really cool part, I think. The bad news was the lower bound, but the upper bound for this notion of stationarity, which we call delta epsilon stationarity, is the new notion that we are promoting. For this, we come up with an algorithm that is guaranteed to attain this delta epsilon stationary point with some kind of dependence. And the structure of this algorithm is inspired 100% by methods like Adam. However, in our case, those choices that were ad hoc, without rigorous theory behind them in empirical land, they end up being theoretically necessary for our method to work, which I find pretty surprising. It means I'm still not fully, I don't think I fully understand, because this was a sufficient tool. I don't know if it's a necessary tool. So look at a scary looking pseudocode, or maybe not, depending on, if you like pseudocodes. But I just want to point out to you some key ideas. You've heard that, momentum is very widely used, right? Adam, M stands for momentum. So momentum is very widely used. So we use momentum, and I'll tell you quickly where we use momentum, and that's really a cool thing. And we use adaptivity, which basically means don't use a constant step size, use a step size that is estimated based on past gradients. That's what Adam is doing. So we use an adaptive step size to be able to satisfy the delta part to come of a stationarity condition. Then some kind of random sampling along a carefully chosen line segment is used to overcome non-differentiability. And then momentum, look at that. It's a beta is a number between 0 and 1. So it's beta time mt plus 1 minus beta times some gradient. Well, this is a convex combination. This convex combination is made to respect the convex hull constraint there. So somehow the structure of the momentum step, the adaptive step, and the additional ingredient here is the randomization. So even though this is a stochastic method, it's a randomized stochastic method. They come together to give you a method that can actually find for you a delta epsilon stationary point. So there are two, but I still find it really worth wondering about further, or maybe somebody manages to think of a better explanation. But these ad hoc choices of adaptivity and momentum end up being really essential here for us to make the method work to satisfy the theory. Of course, it would have been the best possible story if this had been discovered first, and then this method, which would be fine-tuned to yield Adam, but that would be like, theory came first. But I'm happy with this route. You first look at the empirics and then develop the theory for it. And there's been some follow-up works which try to make our method even more implementable by these guys, which is nice, very readable work. And as a result, we finally managed to complete that table and show that to come to a delta epsilon stationary point, this is the kind of complexity in blue color here you need. And the dependence on delta is unimprovable, but I don't know if the dependence on epsilon is improvable or unimprovable. That is a to-do. So this was surprise one. 1A was that everybody was ignoring the non-differentiability. That was a surprise. The actual surprise was that, well, if you don't ignore non-differentiability, you cannot even get stationarity. That was the biggest surprise. And then the third surprise kind of is, well, you can introduce a more general notion of stationarity. And then the surprising thing is an Adam-like method ends up doing the job, which is pretty cool. So that was surprise one. And it took up most of my time because surprise two is mostly empirical. And I will share that with you now. Okay, after a moment's pause, let's look at surprise two. Because here, the story is just beginning to unfold. Even though we discovered this now, I guess, almost a year ago, it's we are, and some of our collaborators are, and I hope some of the people in the audience managed to understand this surprise a bit better. So here is the surprise. So now let's imagine that surprises are not coming due to non-differentiability. So for instance, okay, you're using some kind of infinitely differentiable transformer style model or something. Is there still a surprise left? Indeed, there is still a remarkable surprise left. So here's the difference. Theoretically, we are studying convergence rates to stationary points. That's been the bread and butter of non-convex optimization theory. Empirically, when you train a neural network, you typically just look at either an estimate of the training loss, or you look at the validation loss or something, but you look at losses. You see, okay, this is how the loss is evolving. And so there's already a gap here, right? Does the theoretical quantity align well with the empirically important quantity called losses? And I mean, I'll let you wonder about it. I'll pause for at least like 10 seconds. So to let the audience wonder, conjecture, etc. before I move on. In a live audience, of course, I'd see you getting disturbed, hopefully, by this. So I want to make you a bit more disturbed from next slide onwards. Okay. These quantities don't always align that well with each other. In the luxury of so-called over-parameterized models where you're able to somehow even magically SGD is able to get to a global optimum, etc., there eventually they will align. But for very large scale models in difficult data, stochastic data domains, or just very large models on large data, we are not reaching that regime. And this interesting stuff is happening. So this is, notice it's large-ish data, ImageNet. and a large ResNet, 101, which is really large. So the training doesn't seem to converge to stationary point. This panel shows that the loss is going down. Here maybe step size was changed. And these are the epochs. And this is run for 90 epochs, which many of you may know is kind of standard number of epochs people run ImageNet for. So the loss seems to be stabilizing. Look at the gradient norm. The gradient norm is 0.4 is a big number, right? It's, of course, you're not going to go to 0. This is a computer, but you're not even coming epsilon close. Where is it going? It's just kind of stuck. And it's not because we used very large learning rates. It's not because of the step size. You shrink the step size. Well, you make the step size smaller. See, this is smaller. The loss goes down more smoothly, as you may kind of expect. The gradient norm actually is even worse here. Look at the y-axis is 0.6 here. Here it was 0.35, it was 0.3, right? It's not converging to a stationary point. So this phenomenon is persisting here. And it's not because we didn't train long enough. 90 epochs was standard, you run it for 300 epochs. You see that loss is hardly doing anything, but the gradient remains kind of stuck. So it's not because of insufficient number of training epochs even. And it's not, as I said, it's not the ResNet had ReLUs. We pretended they were not there like many others. And it's not because of non-differentiability. You use transformer XL large model in an NLP task. That's a really large scale problem here. So training loss is going down much more stochastically, but it is going down and kind of stabilizing. Gradient norm seems to be even increasing. It's fluctuating like crazy. So this phenomenon persists. So the question this raised for us was, well, so is it then trying to find stationary points itself is misleading? Well, I wouldn't say it's misleading in all cases, but in several of these very large, challenging optimization problems, it seems if we are developing theory to reach a stationary point faster, that does not necessarily imply that you're able to train your neural network faster to shrink its loss commensurately fast. And now, that's why I said, we are back to square one in mathematical design of algorithms, that you're not even going towards f prime equal to 0 that you learned in high school. So where are you going? And if you don't know where you're going, should we define convergence? What does convergence mean here? And how should we study convergence rates? So it kind of opens up by revisiting this very basic thing. It opens up a bunch of questions for us. And you look empirically what happens to the loss. So if you just were to look at the loss at kind of the last iterate, that is going to be fluctuating. It's not going to converge. But if you take average iterate, then loss does go down more smoothly, which suggests that, okay, some kind of averaging, which in other words means some kind of distributional thinking is needed rather than just the convergence of the parameters. And we have a very rough kind of theorem. It's beginning work. It's far from where you'd want to be. What we say is the following, which is a weak result, yet at least it's introduces mathematical formalism trying to study the whole phenomenon that I showed you. And what is that saying? This result is trying to explain that picture of the convergence of loss. It says that as you run longer, the per iteration change in the training loss goes to 0 without requiring assumptions on smoothness and so on. In particular, it does say we use a neural network that has batch normalization so that things kind of remain in a compact set. Then we say that in expectation, eventually the per iteration change, expected per iteration change shrinks. That's roughly what we are saying. And well, that's a sanity check because that's what we observed empirically. But it's not enough, right? So what this theorem is saying, well, it has very general assumptions because batch normalization is commonly used, okay, and you manage to somehow have compact set. If you didn't have batch normalization, but you could ensure a compact set through some other means so that the parameters are not walking off to infinity, that would be also good. But it's not assuming things like bounding the smoothness or assuming Lipschitzness or assuming that you're in an over-parameterized regime. It's not assuming any of those simplifying things and get a non-asymptotic rate, which was the main thing in terms of progress. And this you can apply to other architectures, without batch norm, or you may have architectures with attention layers like transformer and so on. So you can try to do this theory for various architectures. But the problem, because this theory is very rudimentary, is it doesn't really tell us what is the distribution of the weights, what is this convergence. So I left out the math here about the little bit of, it uses some theory of ergodic dynamical systems, etc. But I kind of left that out. The point was, the parameters themselves are not converging, but some kind of time average of the parameters is converging to some kind of empirical measure. And so what is that distribution that you're going towards? Can you try to understand that? And more importantly, however, what is happening is the slew of questions that it opens up. So because the change converges to 0, so we showed that, non-asymptotically at the rate 1 by square root n, the change in loss is going to 0, but it doesn't mean that the loss itself has a limit, right? It could be oscillating also a little bit, fluctuating. And okay, the parameters, they go towards some kind of distribution, or maybe they are entering some orbit, or I don't know what they're doing, but where are they going? What are their properties? And how should we understand the convergence of the parameters so that once we understand their convergence, how can we then use that theoretical understanding to design methods that can give you lower training loss? And in particular, maybe give that lower training loss faster than existing SGD type approaches. Even harder question, which I think some of my colleagues are investigating some directions along that. The training, etc., is fine, but what impact do these insights, these non-convergence phenomena, what impact do they have on generalization, on unseen data? How can we control that? How can we model that? And where do your iterates go? What is this kind of equilibrium or whatever, orbit or whatever, where you go? How does that depend on your neural network architecture? How does it depend on the optimization algorithms you use? What are the other things that govern it? Because as we understand the optimization side better, we will manage to then maybe also better understand how does the architecture and how do the optimizers, they influence generalization, which is a key important open question in deep learning, right? And you can check the long version on arXiv, but really at this point, the surprise too was to just show you this non-convergence phenomenon and to bring it to your attention and hope that maybe some of the audience manages to develop some new ideas to understand and explain, or at least build on this phenomenon and discover potentially new training architectures and algorithms. So with that, I'll stop here. And now I think we have the Q&A session. Thank you.
Thank you very much, Suvrit, for the fantastic talk. I was certainly surprised by the results. And I have a couple of questions, but I'll wait for the audience to enter
Sure.
their questions. So there is one question from Varun Krishna, which says, what is the practical implication of your version of Adam? Does it converge faster than Adam for non-convex problems?
Oh, I see. So the practical implication is that it converges very similarly. However, the crux is that it is discovered from theoretical principles. It's kind of very rare to discover a method from theoretical principles that ends up kind of working as well as the highly empirically tuned methods. That's kind of the takeaway. Because the earlier part I tried to motivate that the methods that are typically discovered using theory, like variance reduced stochastic methods and other kinds of methods, they work very well in theory, but not necessarily in practice. So one more implication could be, once we understand what should we try to converge to, because our version of Adam is kind of more designed to go to that stationary point. But the second part of the talk, the second surprise is saying that should we even be going to that stationary point? So once we understand that better, then we have a chance to discover an even better method. So here really, yeah, so I'll just repeat once again, greatly trying to shrink the theory practice divide to build theory which does explain what's happening in practice, but also looks at practice to figure out a new direction for theory itself.
Thank you.
I have a quick question, Gauri.
Sure.
So in the second part, you mentioned this, the gradient doesn't go to zero, but I was wondering the type of examples that you gave, the parameters probably were in the millions, right? The number of neural network parameters.
Right, those are huge networks. Those are really
Yeah. So which means the gradient is a vector of size several millions.
right.
So when you say the norm is not close to zero, it could be because just that each component would be extremely small, but when you're adding up a million of them, maybe they're not. So I guess I'm asking whether it's really not zero or is it just a numerical?
Yeah, no, actually, Srikant, I'm glad you asked that question, because when first time we looked at it, we asked, like, we posited like 6 to 7 different hypotheses, including numerical issues and all those things because of very large vectors. And in the paper, we kind of discuss and kind of rule all of those out. So it's not really, this was my instant gut reaction also when I first saw the empirical result, that wait a minute, it's just a giant vector, add together a billion epsilons, it looked like 0.4.
Right.
But we kind of ruled that out experimentally. So we did very thorough experiments to make sure that this is a repeatable of actually occurring phenomenon, and it's not a made up phenomenon. But I think along the line of the gradient, I think the in some sense, the loss, no, so it's like, because we are trying to get a non-asymptotic understanding, it's more pronounced. Now, if you were to let this run up to infinity, and you would also keep decreasing the step size to 0 in the usual non-summable manner, then of course convergence has to be forced.
Right.
Yeah. But yeah, so I think it's a very valid thing to worry about, and that's we rule that out. There's a few other kind of things that along that direction, I don't remember, but I remember writing down a list of at least 7 potential alternative hypotheses.
Okay.
That we ruled out. Yeah.
Thanks for the nice talk.
Yeah. Thank you.
I think we have time for maybe 1 or 2 more questions. So there's one question from Pranay Sharma. He's asking that you mentioned that it is difficult to verify stationarity in the non-convex, non-smooth setting. There is a similar result about verifying the saddle point for a smooth non-convex non-concave min-max problem. So is there a parallel between these two?
That's an interesting question. So if you were to look at a smooth, non-convex, non-concave, and because it's a min-max, if you treat the max part as a black box, then the minimization problem starts to look non-smooth. So it morally looks similar. However, here you know a little bit more about the structure because it has an explicit min-max structure. So because you know a little bit more about the structure and you know that lower bounds are often delicate, it's I can't 100% say the same result should hold. The presence of min-max, the knowledge of explicit structure on how the maximization arises, that could allow you to potentially circumvent a lower bound, but I'm not sure. But it's definitely, yeah, it could be that it ends up suffering from similar kind of lower bound in terms of, I'll make a side comment also in terms of, getting to some kind of local Nash equilibrium. So there is a result, probably you may have seen, there is a paper by Manolis Zampetakis and my colleague Kostis Daskalakis, and maybe they have co-authors on that, which tries to study the kind of NP hardness / interactability of getting to a local Nash equilibrium, which would really correspond to the problem that you talked about in terms of smooth, without worrying about non-differentiability. So there is some interactability result already there, but that's for, but the thing is that is for Nash, local Nash, and if we weaken that to something, I don't know what is a good weakening of that that exists, for which you may get a similar negative result.
Thank you. I have one quick question.
Sure.
So you define the relaxed notion of stationary point.
Yeah.
So there's a bunch of work in deep learning about evaluating the quality of a stationary point or local minimum. So do you have a sense of what is the quality of these relaxed stationary points? Like in experiments, did you observe how good they are?
Yeah, sorry, I don't have a speculation on that, because we didn't kind of try to judge the quality of where we are landing experimentally. But the way we validated this was in the kind of same way you see when we had that randomized stochastic method, which is guaranteed to get to this delta epsilon stationary point, but then empirically it is validated by just comparing on benchmark data sets compared with other solvers like Adam, etc., to show that it is reaching essentially the same place, which means if we have understanding for SGD plus momentum or Adam or others about what kind of stationary points they're reaching, seem to be reaching, then similar understanding should likely translate to our case. It may be potentially even easier, a little bit easier in our case, because there's a little bit of extra randomization, which could save you, but I'm not sure.
Thank you. Thank you very much again for the excellent talk. And thanks to the audience for the questions.
Okay, thanks. Cool. Then thanks for having me, and see you next time at some other C3 AI event.
I hope so. Thank you so much again.
Bye.